Okay, so we're going to actually do something useful today. So far, a lot of the stuff that we've talked about is sort of theoretical. It doesn't look like a real pulse sequence. So the thing I'm going to talk about today is an actual real pulse sequence that we would use, and so it's generally called, it's called a lot of different things, but let's just write up some of them. So it's often called flash, which means fast, low angle shot. And then but another company couldn't use that, so it's also called SPGR, which stands for spoiled grass, and grass stands for something else. So you might wonder, like, well, what is unspoiled grass? So there's grass, which is like gradient recalled echo in the steady state or something like that, and that's unspoiled grass. But of course you couldn't call it. The other company couldn't call it that, so sometimes you call that SSFP. So all of those are all words in the MRI language that you'll see if you look at any articles. And so there's basically spoiled versions and unspoiled versions. So, and I'll talk about the SSFP a little bit later. But the spoiled versions are quite spoiled, unspoiled. The spoiled versions are one of the most common sequences that are used in MRI. And so what I'm going to do is draw out the whole pulse sequence, all the different gradients, so you can get an idea of what it looks like, a real pulse sequence, without really explaining it yet. But we'll come around a couple of weeks from now after we've talked about the Fourier transform and actually kind of describe it a little bit more. So to draw out the pulse sequence, we always have 5 lines. So there's the RF stim, and then we have the 3 gradients. So because those can all be controlled independently, and then we have the signal that comes out. So this is RF sig, and here's the X gradient and the Y gradient and the Z gradient. So I'll draw, this is still not a completely practical sequence because this is just a 2-dimensional sequence. This is actually very similar to the localizer that runs when you start up the scanner. So since it's a low angle, fast low angle shot, we'll have an alpha pulse here, so not a big pulse like a 90 pulse, and we'll explain why we want to do that. And so then we have to sort of do a slice select. So here's our slice select. We didn't explain how we do that, or why it looks that way, but we'll talk about that. Talk about that later. And then we have some phase encoding. Remember, I didn't say what that is yet, but that's a bunch of different, that means like do it over and over again with all these different settings. That's what that symbol means. And then we have our readout. And so then here's our readout, like that. And then we've got a spoiler. So what's the spoiler? So one of the things. So what's the overall? Well, let's go until we hit the next alpha pulse. So here's another alpha pulse. And so that means that this is the TR. And then remember the echo is going to come, here's where the gradient echo is going to, so here's the FID, and then here's the gradient echo. And so this time here is the echo time like that. Okay, so that's the full sequence. And so now we select the slice again, do some more phase encoding again, and then do another readout and maybe another spoiler. Okay, and so and from that we would get another signal here, and then another echo over here. Okay, and we're going to look at particularly at this time point right here, just right before, and then this time point here, just right after. So I'll sort of highlight those in advance. So those are 2 time points that we're looking at in our equations to try to figure out what the brightness is. Okay, so what's the, I just drew the sequence without much explanation. So what's the general sort of theory of the fast low angle shot? So the general theory is that we want to, if we do a 90, so if here's our starting magnetization, if we go all the way to a 90, what happens is we have 0, so that's the longitudinal direction and the transverse direction. So if we go all the way to 90, we've got 0 longitudinal. And now it's going to take a couple seconds to get back up to regrow that T1 regrowth up to the MZ0. MZ0. So that's a problem, especially if we want to collect, 16 million data points, and that's how many data points are in a high resolution anatomical scan. 16 million data points. So we can collect, say 256 data points across the echo, but that still means we've got to do 16,000 echoes. So if we're going to do that, we're not going to be able to do that just waiting around like 2 or 3 seconds at a time. And so the idea of fast low angle shot is if we just do, say, like a 10-degree flip angle, what happens is we save, so here's how much we started with, but we've only we've only lost that much longitudinal magnetization. And yet we still get a sizable amount of transverse magnetization. It's not as much as a 90, but because of the way the cosine function looks, so this, this amount of transverse magnetization that we get is going to basically be equal to the sine, but the amount of longitudinal that we killed is going to be proportional to the cosine. So if we look at our cosine function, then we have something that looks like this. So that's a cos. So that's 1 minus 1. And so basically the amount that we kill here, that distance, is going to be proportional to where you are on the cosine curve. So if you don't do any flip at all, you don't do anything. But if you do a small flip, you'd still hardly do any damage. Whereas this one is proportional to the sine. So what is the sine? Well, if we put the sine in that same graph, here's the sine. So basically, if we stick right here, what's going to happen, we won't lose much because of that cosine, but we'll gain quite a bit because of the sine. So that's the rationale. So we won't have lost much longitudinal, but we still got quite a bit of transverse, and so we can so we can hammer away at a much higher rate, fast low angle shot. So that's the principal idea behind the sequence. So to write out the equations, we've got to start with the block equation solution. So use block equation solution for T1. So we haven't talked. We're just mainly talking about how much longitudinal magnetization we've recovered, because we're gonna be in a steady state where we're not ever recovering up to the full magnetization. So that's the steady state. Yes. Okay. So the first equation is the equation for here. So we'll put that. I'll put an A here. So that first equation is going to be just the block equation solution, and it's a forest of subscripts, but I'll explain all of them. So it's mz for the nth time point, because we have to sort of consider steady state, so we've got to consider multiple cases of this at a time just before the next RF pulse. So that's why we're just before. That's the 0 minus business. And so what that's going to equal is basically our amount of recovery, and the first term in the block equation solution is basically 1 minus e to the minus tr. So we recovered from the previous. So this guy is n, and this guy is n minus 1. N pulse number. Yeah, I didn't put that in last year. It's clearer. So this is the nth pulse, and this is the n minus 1th pulse. Okay, so this is tr over t1. And then we have another thing in there, which is however much magnetization we started with. And if you look at how much magnetization we started with, that's going to be whatever was there right after we did the previous pulse. And so that's going to be plus whatever not mz0, but plus whatever magnetization on the n minus 1 pulse right after we did it. That's the 0 plus. And then that's times, because we're now trying to figure out this point, we have to decay that one. And so that's also decayed by tr over t1. Okay, so that's our first. So all we didn't do any. takes 5 minutes to write out one block equation. So it's just the solution to the block equation, but just applied to this pulse. So the amount of longitudinal that will have regrown here is this one, which always starts from the equilibrium magnetization. So it's that one plus whatever we started with decayed. So whatever we started with was this amount decayed by however much time between here and here. So now we have to sort of consider the actual flip angle. So assume small flip, and so what is that going to be? That's going to be so here's our small flip, and here's our alpha. That's our flip angle, And so basically we want to know, this distance and distance, those two distances. And so this guy, the amount of longitudinal we have is going to be, cosine of alpha, because that's the adjacent side on the right triangle. So here's the okay. So if we assume there's a small flip angle, then we can look at this equation. So MC. So essentially what we're trying to do is just figure out that guy. So what is that guy going to be? We just wrote it there. We didn't say like what it was. We just said whatever it was that we started with. And so in order to figure out what that is, we have to figure out how much our flip is going to leave of the magnetization. So that's really what we're trying to figure out now. Is this one only depends on our equilibrium magnetization, so we just copy that one again. But now we're going to substitute something in for that one, and the thing we're going to substitute in for it is basically our unknown magnetization right before the pulse times the cosine of the flip angle because of our small flip, decayed the same way we did before. Okay, so we still got a lot of unknowns here, but the way we solve the problem now is we just assume in dynamic equilibrium. And so what does that mean? So assuming we're in dynamic equilibrium means that we've done enough pulses, and so we've got to a steady state. We've got to a steady state here. And so if that's the case, then this unknown magnetization right before this pulse, which is actually another number, it's right here. Okay. So that's this guy here. So here's A. So this guy is, we'll call that guy B. And this guy is C. So this guy is C. So that's our unknown magnetization before the previous pulse, and here's our unknown magnetization before the current pulse. So if we're in sort of dynamic equilibrium, then what we want to do is basically assume that those two are the same. So what is assume we are in dynamic equilibrium mean? It just means that this guy, the current right before the current pulse, is equal to this guy right before the previous pulse with no cosine. So that's the meaning of this. Assume we're in dynamic equilibrium. So now what we can do is we can just say this number and this number are the same. We don't know what they are, but they're just the same. And so it's a good exercise to just do the simple algebra that will give you the next equation. So the next equation is what is the longitudinal? Because we're going to eventually have to consider the transverse. So what is the longitudinal? the longitudinal is going to be, and so in the notes we just write this as the mz steady state right before a pulse. So if we solve for the mz steady state, because now these two things are the same, what do we get? So basically, with this simplification, or just the assumption that these two different numbers are the same. So what we get is, so this is the longitudinal. So it's mz times 1 minus c to the minus tr over t1 over 1 minus cosine of alpha times e to the minus tr over t1. Okay, so that's our equation now with stuff that we do know for this unknown amount of magnetization right before the flip. So if we look at this, we say, we know mz, we know what the tr is, we're assuming we know what the t1 of the tissue type is, and we know what our flip angle is. Okay, so now what we're really looking for is what is the amplitude of this echo here. So this is the number we're really looking for. But that number is TE later. And so since we will have generated transverse magnetization, it's going to be decaying with T2, and so we have to use use T2 solution to block equation. And so if we do that, what we end up with is the amount of XY magnetization, because what we did is we had some amount of longitudinal, that's this guy. So sorry, make sure I get the Z in here. Yeah. So we had this amount of longitudinal that regrew, and this is how big it's going to be. But now we're going to actually turn some of that into transverse, which will decay. And so that's going to now decay. So we have to consider how much of it are we turning into transverse. So if we look at our diagram here, so here's our flip. So in this case, we found that the cosine is what gave us the amount of remaining longitudinal, but now over here is going to be the sine, and that's so mt. So the portion, so we need a sign in there because we have to multiply this thing by a sign, basically, because we're not turning all of the longitudinal into transverse, just however much, however much according to whatever the flip angle we did was. So what does that boil down to? So that will boil down to the amount of XY magnetization, which is really the thing we want to know. Like what is the XY magnetization at that echo point? And so the amount of XY magnetization at time TE. So we could calculate it for some other time, but for the current point, for the current purposes, we just care about like what is it? What is here at the center of K space? So what is that? And so So how do we get to xy, and why is it xy? It's x prime, y prime, because we're in the rotating coordinate system, so we don't have to worry about the precession business. It's the amount of recordable xy at time te, and what's that going to be equal to? It's going to be equal to same thing we had before, the amount of transverse that we recovered to minus tr over t1. And that's divided by the same thing, 1 minus cosine of the flip angle times e to the minus tr over t1 again. But then finally, we've got to decay it with the T2 solution. And so what's that going to be? That's going to be multiplied by the sine, because we just have to consider, the amount of transverse. We're not turning, all of the longitudinal into transverse, just a part of it. So that's why the sine is in there. And then we have to multiply by e to the minus t te, because it's the amount of time we decayed over T2 star, because this is a gradient echo. Okay, so that's our final answer, final useful answer. So now let's we can just plot that equation out to see what's going on. Now before we do that, we have to sort of consider all of the things in the equation. So what are the things in the equation? Well, we have the things that we can change in the pulse sequence, and so we can change, TR, we can change, TE, and we can change the flip angle. So here's the flip angle. So that's what I always say. These are the knobs on the scanner that we can that we can change. What are we actually getting? We're getting one number. So we have 3 knobs on the scanner that we can adjust, and then we've got 3 different properties of the tissue. And so the properties of the tissue is this is basically the proton density, because the amount of longitudinal magnetization is just proportional to how many spins you have, so that's proton density. And then we've got the T1, and then we've got the T2 star. So T1, T2 star. So these are tissue properties which we're trying to image. Like, for instance, T1. So you can see what the problem is here. I mentioned this last time when we talked about the spin echo. We've got one data point. We've got 3 different knobs that can control the data point, make it bigger or smaller. Typically, we're going to want it bigger so we get a big signal. But unfortunately, we've got 3 unknowns. So these are unknowns. So we've got 3 unknowns, but we only got one number. So not so good. That's why all scans are, that's why you say we're doing a T1 weighted scan. What does that mean? It just means that we've somehow fiddled with this equation so that T1 is the main thing that affects this number. We've adjusted the knobs in such a way that we're going to mainly make T1 affect this number. That's what a T1 weighted scan really means. Whereas a T2 weighted scan would be, we've fiddled with the knobs in such a way that T1 doesn't make as much of a difference to this number, and T2 makes a bigger difference to the number. Now you could imagine there's other ways of doing this. One way of doing it is, what if we collected a whole bunch of data with different settings of the knobs so that we had multiple data points over here? Then we might be able to solve for what the T1 and the T2 star and the proton density of the tissue was. But this sort of gives you some idea of the size of the problem. So there's 7 things to keep in mind. So 3 knobs, 3 tissue properties, and then one data point that comes out. Okay, so what does that look like if you actually plot that, so that we can sort of get an idea of what what tissue contrast looks like. Okay, so if we just plot this equation, so you could just plug this equation into MATLAB and plot it. So, what does it look like if you do that? But we've got 7 things, right? So we'll plot one thing on the y-axis. We'll put this guy on the y-axis. But now we've got 7 things to deal with. And so let's just make some assumption about what the T1 and the T2 star and the proton density are. So we'll just give them some numbers, practical numbers that, taken from the literature for white matter, say, or gray matter. And then now we've still got 3 knobs. But we've only got one axis here because we're two-dimensional people, two-dimensional map people that just have sort of two-dimensional maps of things. And so what we're going to do is we'll just set 2 of the knobs and just vary one of the knobs. And the knob that we're varying is the flip angle. And it turns out if you mess around with this equation, the flip angle is the one that has the biggest effect on the contrast between different tissue types. And so let's just plot out what the signal, so this is basically the signal. So that's, it's this number. I'll just put it there. So m in the rotating coordinates, x, y at time of echo. So that's the signal. So what does that look like? It might look something, so if there's 0 flip angle, you're going to get no signal. So it will come up like this and say do something like that. And, this might be, say, about 30 degrees. So as you go up, we're generally in the sort of low angle, the fast low angle shot regime. So let's just say, for example, that was the gray matter. So this thing right here, the maximum, this is called the Ernst angle. And that's a useful thing because if we're doing a gradient echo, we always want the largest signal that we can get. And so we don't want to do a flip angle of 1. That would have almost no signal. It'd be a very noisy image. And if we do a flip angle of 60, we get almost 0 again. So the Ernst angle, you can write an equation for the Ernst angle that will tell you, like, what is the flip that will give me, for this setting of all the other knobs, give me the most signal. But it turns out that's not what we want. So what is the problem? Well, the problem is here's another tissue type. So, and it sort of looks the same. So if we enter the tissue parameters for white matter, we might get something like that. So now what are we actually looking for? We want contrast. And what is contrast? Contrast is, the difference between these 2 guys. And so actually what we want is contrast. So if we plot that difference, we're going to get, say if we plot, how did I plot it? I plotted it white matter minus gray matter. So if I plotted it white matter minus gray matter, it's going to be 0 here, and it's going to be negative here. So it's going to be negative here like that, and then 0 here, and then the peak is going to be probably somewhere like about here, something like that. So this is the contrast, which is what we're really interested in. White matter minus gray matter. And so that will tell us what is the Ernst angle will tell us what the biggest signal is, but what we want is the difference between these two. So two sets of these equations with different settings for the tissue. For the 3 unknown tissue types. And what we want to know is like what is that difference? What is the maximum of that guy? And so here's what we really want is this point. Where is the most contrast? So max contrast. And it's interesting when you look at this. So it's possible if you accidentally set the flip angle to where these curves cross, you get 0 contrast. If you actually go below that point, you'll actually get the reversed contrast, and it'll make the gray matter brighter than the white matter. So if you just change the flip angle by like 2 or 3 degrees, you could suddenly completely reverse the contrast of your image. So yeah, so when you go on the scanner, you'll have some flip angle like 7 degrees or something, and that one really works out well, and you're all happy. But you ever wonder like, what if I put in 6 over there? What about 9? What would happen? So this is what's happening, and we got that from starting with very simple assumptions about the Bloch equation, assuming that we were in this equilibrium, putting in the T2 star decay, get this whole mess, and then you can plot it. And that's part of the assignment, is to plot out, just take this equation and plot it out for different tissue types and just do what I just did right here in MATLAB. Okay, so that was useful. That's an actual real pulse sequence. And so I'm now going to talk about another useful thing, sort of signal to noise. So we could go through a lot of math that I don't fully understand in order to sort of come up with all the rationale, but what we can do is just hit the take-home points of signal to noise. And what is signal to noise? Well, it's more than just signal. So here we're just plotting sort of the signal size, but there's signal to noise is, so signal can vary, but so can noise. And so one of the things we want to do is determine when we change different parameters in our sequence, how does that affect not just the signal, but how does that affect the relationship to the noise? And so we should just quickly define what the signal to noise ratio is. So signal to noise ratio. So sometimes SNR or S/N. And basically we're just defining that as the average signal. So sometimes we just put a dash on top to mean average. So this is the average signal over the standard deviation of something that's not an object. So this is the average object signal, and this is the standard deviation of some non-object. So for instance, you might just put a phantom, just like say a ball into the scanner, and then just ask, okay, what's the average brightness of that signal? That's just the average pixel value that comes out. And then what's the standard deviation of the air. So here's the here's the standard deviation of the signal in the air. This is the the average brightness of something that's in the object. So that's what our signal to noise is. So that you can see that's different than the signal, because you could have the same brightness image, but the background could contain a lot of noise, a lot of speckly noise, or it could be pitch black and have very high signal to noise. So the noise would be very low. So that's our very simple definition. So it's you just average the pixel values somewhere in the image, and then you go out to the air where there's basically no signal, and then you measure the standard deviation of those values. And so what controls that? And so here's the signal to noise ratio per voxel is proportional to first the voxel size. So it turns out the voxel size is just overwhelmingly important. Most people who use MRI don't realize how important this is. So this is the voxel size. So let's just run some simple calculations. If you have a 3 by 3 by 3 voxel, that's 27 cubic millimeters. 3 by 3 by 3. If you have a 2 by 2 by 2 voxel, that's 8 cubic millimeters. So that means going from a 3 by 3 by 3 to a 2 by 2 by 2, 1/3 your signal to noise. You got 3 times as much signal to noise to go from 2 by 2 by 2 to 3 by 3 by 3. So voxel size is really important. But what else is in there? So what else is in there is, very unfortunately, under a square root sign. And one of the first things, I didn't go through the derivation of this, I'm just presenting it, but one of the first things that's under the square root sign is the number of acquisitions. So the number of acquisitions is under the square root sign, so that means, say we halved our signal to noise, we couldn't make up for that by just doing 2 scans, because this is under the square root sign. So we'd have to do 4 scans. So in order to make up for it, because the square root of 4 is 2, and then that would make up for our smaller voxel size. So let's work through that. If you work through the 2 by 2 by 2 versus 3 by 3 by 3, you're basically going to need 27 cubic millimeters over 8 cubic millimeters squared. So that's about about 9, equals about 9. So that means going from a 3 by 3 by 3 to 2 by 2 by 2, you've got to do 9 acquisitions to equal 1 3 by 3 by 3 acquisition, the same signal to noise. So the voxel size is overwhelmingly important. The other thing that's on this side is the number of pixels. Now that you might think that's kind of weird. What does the number of pixels have to do with anything? But the number of pixels corresponds to the number of data acquisition points. So if we collect 16 million points in K-space, we get 16 million points in our 3-dimensional reconstruction. So this is the number of pixels. So number of pixels. So you collect more pixels, you get more signal to noise, but it's under the square root. This you can think of as the number of reps. How many repetitions did you do? And then last but not least, there's the bandwidth, or the inverse of the bandwidth. And so we'll try to explain what's going on there. So this guy, that's another thing you can set on the scanner. You can set the bandwidth on the scanner. So this is the delta t is the read time step. We'll see that the bandwidth is the inverse of that. So what does that actually mean? Well, what that actually means is here's our echo coming in. Okay, so That's our echo coming in. Now when the echo comes in, we record it, we digitally sample it. And so what we do is we make a whole bunch of samples of that recording. What does that mean? For each sample, we just go up in time to our echo, continuous echo coming in, and we just say, well, I'll take that value. And then I go up there, and I say, I'll take that value. So these are our samples, data samples. Each one is a complex valued. Remember, it's a complex valued thing, but whatever, data samples, okay. Now, so what's the bandwidth? So this amount of time right here, that's delta t. So it's the read time step. So how much time in between the read time step, and that equals 1 over the bandwidth. Or alternatively, the bandwidth, equals 1 over the read time step. Same thing. So what does the bandwidth mean? Yeah, again, this is so when the physicist, when I talk to the physicist, he said, it's just that this lower bandwidth is going to have higher signal to noise. So that's just, they just knew that, So if we make this smaller, we get less signal to noise. What does shorter mean? Shorter means a higher bandwidth. So, so if we make delta t bigger, that means bandwidth is lower. But that turns out to be good. So a bigger delta t, lower bandwidth, is more signal to noise. And so why is this? And what does bandwidth mean? So one of the problems is whenever we sample something, so whenever we digitize something, one of the things we have to watch out for is we have to make sure that we remove any frequency that is more than half as big as our sampling rate. And you can see what the problem is. If you've got say we had like a really high frequency signal in here like this, going up and down very rapidly like that. If we sampled that, we might just nail different parts of this oscillations going up and down and get a fake signal that's actually not the real signal. And so the rules are when you're sampling is you have to essentially roll off. So this is frequency here, and there's also negative frequency. This is negative frequency. We'll get to that later. And so bandwidth means like how wide is this thing? That's why it's called bandwidth. So this, you basically have, this point has to be, half of max data freak. Why is it half? Well, if you're half, you could sort of catch the top and the bottom of like a sine wave. Whereas if you're the same frequency as the sine wave, like once every sine wave, well, then you're just going to get different parts of the sine wave randomly on different cycles, and that's going to be a mess. So you need to sample at least twice as fast as the biggest frequency in your data. And so what this guy is a high bandwidth, which means fast sampling, which means we have to let in a lot of noise. And so if we look at a low bandwidth scan, we would record the data, spread this data out, recording of the data out further. So what we would do is we would just sample it like this. That's low bandwidth. High bandwidth. And if we did that, then what we can do is we can move the filter down, because we no longer, so we no longer have to sample very rapidly because we're filtering out any junk that's higher frequency, and so we can sample at a lower rate. And so what happens is, when you do that, you will remove noise. So when you move to a lower bandwidth, you filter out more noise. So that removes noise. Because there's noise in the environment of all kinds. And if we just filter more of it out, we're just going to have more signal. So like, if you're like me, when you first heard that, it said, like, I sort of get it. It sort of seems sort of logical, but that's why a lower bandwidth. So you might say, why don't you just do a low bandwidth all the time? Well, the problem is, if you sample over a longer period of time, you're going to have more time for B0 defects to mess up your signal. And so a lower bandwidth will scan will have a better signal to noise, but it will have worse distortion. And so there's a trade-off. There's a very straightforward trade-off there. But this is actually one of the few useful things I've taught you in this class. Kind of like, what is the actual signal to noise per voxel? How is it affected by the main things you can adjust, like voxel size, number of repetitions, how many pixels you have in your scan? That actually is a strong effect, and then what the bandwidth is. And these can be varied. Sometimes if you're not in a part of the brain that's very distorted, you can go to a lower bandwidth and get more signal. Okay, Stan, I think we're ready to stop. I'll take some questions so we can end the recording now.